Somewhere in the cosmos tonight, there exists an object so terrifyingly massive that if you were to fall toward it, time itself would slow to a crawl, stretching your final moments across an eternity. These are the most frightening black holes. Known to science, cosmic monsters that dwarf our entire solar system and challenge everything we thought we knew about the universe. In the darkness of space, TON 618 lurks like a sleeping giant, its gravitational pull so intense that it outshines 140 trillion suns. Meanwhile, our own galaxy harbors Sagittarius asterisk, a 4 million solar mass predator that sits quietly at the center of the Milky Way, just 26,000 light-years from where you rest tonight. If you've ever wondered what the most terrifying objects in the universe truly look like, and what would happen if we encountered them, then settle in as we journey through the cosmic abyss to meet these gravitational monsters that make even our wildest nightmares seem gentle. Before we venture into the darkness together, consider subscribing and ringing the notification bell. These cosmic stories take months to research and craft, and your support helps us continue exploring the universe's most fascinating mysteries. Imagine, if you will, falling through an invisible boundary where the very fabric of space and time begins to bend. Beyond recognition, this is the event horizon, a point of no return where not even light itself can escape. Tonight, as you settle into comfort and safety, we're going to explore what makes certain objects in our universe so fundamentally terrifying that they challenge our understanding of reality itself. What is it that transforms a black hole from a fascinating cosmic curiosity into something that stirs a primal fear deep within us? Perhaps it's the way they violate our most basic assumptions about existence. Or maybe it's how they take the familiar laws of physics that govern our everyday lives and stretch them into something unrecognizable, something that seems to whisper of cosmic horrors beyond our comprehension. Let me paint you a picture of what scientists call spaghettification, a process so named because of what happens to objects that venture too close to these gravitational monsters. In astrophysics, spaghettification is the vertical stretching and horizontal compression of objects into long, thin shapes in a very strong, non-homogeneous gravitational field. Imagine yourself floating peacefully through space, approaching what appears to be empty darkness. But as you drift closer to this invisible predator, something extraordinary and terrifying begins to happen. The gravity pulling at your feet becomes noticeably stronger than the gravity affecting your head, just a few feet away. But in the realm of a black hole, those few feet might as well be light years in terms of gravitational difference. As the astronaut approaches the event horizon, the gravitational difference they feel also increases. As they cross the event horizon and approach the singularity of the black hole, the gravitational gradient becomes exceptionally steep, stretching the object infinitely into a thin, elongated shape. Your body would begin to stretch, slowly at first, then with increasing intensity. Your bones would elongate, your muscles would strain, and eventually, the very atoms that compose your being would be pulled apart in a cosmic taffy pull that defies our most fundamental understanding of what it means to exist as a coherent entity. This isn't the quick, merciful end we might imagine from science fiction films. This is a gradual dissolution that could, from the perspective of distant observers, appear to last forever. But here's where the true cosmic terror reveals itself. Time dilation. As you fall toward the event horizon, time itself begins to slow from the perspective of anyone watching from a safe distance. They would see you growing redder and dimmer, your movements slowing to an eternal crawl, frozen forever at the moment of crossing that invisible boundary. Yet from your perspective, time flows normally as you experience every moment of your spaghettification in real time. This wasn't always something we could visualize or truly understand. For decades, black holes existed only in the realm of mathematics. Solutions to Einstein's equations that seemed too bizarre to exist in reality. They were theoretical monsters that lived in the playground of physicists' minds, safely contained within the boundaries of complex equations and thought experiments. Then came the breakthrough that changed everything. Astronomers have unveiled the first image of the supermassive black hole at the center of our own Milky Way galaxy. This result provides overwhelming evidence that the object is indeed a black hole, and yields valuable clues about the workings of such giants. In 2022, the Event Horizon Telescope collaboration gave us our first actual glimpse of Sagittarius A*, the supermassive black hole that sits at the heart of our own galaxy. Picture that image in your mind, a glowing ring of superheated matter swirling around a perfect sphere of absolute darkness. That darkness isn't empty space. It's the event horizon itself, a region where space is so warped that it appears to our eyes as a perfect absence. The glowing ring is matter, being accelerated to incredible speeds, heating up to billions of degrees as it spirals toward its doom. This result allows us to refine our theoretical models and simulations, improving our understanding of how matter is influenced near the event horizon of a black hole. These recent observations have revealed something even more unsettling: the chaotic, turbulent nature of the accretion disk, the swirling maelstrom of matter being consumed by the black hole. Using 2017 to 2018 data, the EHT revealed turbulence in an 87 asterisk accretion flow, showing us that these cosmic monsters don't consume their prey gently or predictably. The turbulence resembles a cosmic storm, with material being whipped around at a significant fraction of the speed of light. Magnetic field lines twist and snap like cosmic hurricanes, occasionally launching jets of matter thousands of light years into space. The measurements, made with interconnected radio telescopes, also confirm strong magnetic fields close to the black hole's edge. As you envision this scene, let your mind wander to the scale of these phenomena. The matter being consumed isn't just gas and dust. Entire stars, planets, maybe even solar systems are being slowly dismantled and consumed. Each particle of matter experiences its own terrifying journey through spaghettification, contributing to the brilliant, chaotic dance we observe from our safe distance. What makes this particularly haunting is the realization that these events are happening right now, as you rest peacefully, somewhere in our galaxy. Matter is crossing the point of no return, experiencing this cosmic horror in real time. The light from these dying moments is traveling through space at this very instant, carrying with it the last signals from objects that are being erased from existence. The Event Horizon Telescope has achieved something remarkable in recent observations. The Event Horizon Telescope at collaboration has conducted test observations, achieving the highest resolution ever obtained from the surface of the Earth. By detecting light from the centers of distant galaxies at a frequency of around 345 Uz. This unprecedented resolution is allowing us to peer closer to these cosmic monsters than ever before. Revealing details that would have been impossible to observe just a few years ago. But perhaps the most unsettling aspect of black holes isn't their ability to destroy matter. It's their ability to fundamentally alter the nature of information itself. The laws of physics as we know them break down at the singularity point. At the center of each black hole lies a point where density becomes infinite, and space-time curvature reaches beyond our mathematical ability to describe. Here, the very concepts of space and time lose their meaning. This is where cosmic terror transcends mere physical destruction and enters the realm of existential dread. A black hole doesn't just consume matter and energy. It appears to consume the very information that defines what that matter was. If you were to fall into a black hole, it's not just your body that would be destroyed. The information that makes you uniquely you, every memory, every thought, every quantum state that defines your existence, might be erased from the universe entirely. As we drift deeper into our exploration tonight, carry with you this fundamental understanding. Black holes represent the ultimate unknown. They are places where our most cherished laws of physics break down, where causality becomes questionable, and where the very nature of existence itself is called into question. They are cosmic question marks written in the language of space-time, challenging us to confront the limits of our understanding. But these fundamental terrors pale in comparison to what we've discovered lurking in the deep cosmos. The simple stellar mass black holes we've been imagining, formed from the collapse of individual stars, are merely the beginning. Out there in the darkness, objects exist that make our worst nightmares of gravitational destruction seem gentle by comparison. Monsters so massive and so powerful that they redefine what we thought possible in our universe. Sometimes the most unsettling realization is that the danger you've been searching for in distant corners of the universe has been silently watching you from your own backyard all along. As you rest tonight, just 26,000 light years away, a cosmic stone's throw in astronomical terms, something enormous sits in perfect silence at the very heart of our galaxy. Sagittarius Asterisk, our neighborhood monster, weighs as much as 4 million of our suns. Yet it lurks there so quietly that for decades we could only detect its presence by watching the stars around it dance to its gravitational tune. Picture this scene in your mind. If you could somehow travel to the galactic center and float safely in the darkness, you would witness one of the most mesmerizing and terrifying ballets in the cosmos. Stars, massive, brilliant suns larger than our own, whip around this invisible predator at speeds that defy comprehension. The star known as S2, one of the closest orbital companions to our galactic monster, accelerates to over 7,650 kilometers per second at its closest approach. That's more than 2.5% the speed of light. Racing through space in a 16-year elliptical dance of death and survival. In 2022, mid astronomers and others, with the Event Horizon Telescope collaboration, accomplished something remarkable. They snapped the first image of Sagittarius A*, revealing the supermassive black hole at the heart of the Milky Way galaxy. This historic image provided overwhelming evidence that the object is indeed a black hole, and yielded valuable clues about the workings of such giants, which are thought to reside at the center of most galaxies. Imagine holding that image in your mind, a glowing, turbulent ring of superheated gas and plasma, swirling in chaotic patterns around a sphere of perfect darkness. The black hole itself cannot be seen, as light is incapable of escaping the immense gravitational force of a black hole. Only nearby objects whose behavior is influenced by the black hole can be observed. The observed radio and infrared energy emanates from gas and dust heated to millions of degrees. But what makes this image particularly haunting is what it represents: a portrait of our galaxy's beating heart taken from the inside. We are, quite literally, looking at the gravitational anchor that holds our entire cosmic home together. And it is a monster capable of tearing apart the very fabric of space and time. The breakthrough didn't stop with a single image. More recently, astronomers unveiled strong and organized magnetic fields spiraling from the edge of Sagittarius A*, seen in polarized light for the first time. This new view of the monster lurking at the heart of the Milky Way galaxy revealed a magnetic field structure strikingly similar to that of the black hole at the center of the M87 galaxy, suggesting that strong magnetic fields may be common to all black holes. These magnetic field lines twist and spiral around our galactic center like cosmic DNA, creating a structure so organized and powerful that it influences the behavior of matter across thousands of light years. Multiple telescopes, including Chandra, observe the Milky Way's giant black hole simultaneously with the Event Horizon Telescope, giving insight into what is happening farther out. Then the field of view of the EHT, the collaborative effort, revealed something deeply unsettling about our cosmic neighborhood. Sagittarius A* is not the quiet, dormant giant we once imagined. It's an active predator, constantly feeding on the gas and dust that drift too close to its gravitational embrace. Recent discoveries have shown stars orbiting Sagittarius A* appearing rejuvenated after stellar collisions, and high-speed baby stars swarming around the black hole at incredible speeds. What would it feel like to witness this cosmic feeding in real time? Picture yourself floating at a safe distance, though in truth, no distance feels entirely safe when contemplating such a monster. Watching as wisps of interstellar gas begin their final journey toward the event horizon. The material doesn't fall straight in like water down a drain. Instead, it forms an accretion disk, a swirling maelstrom of matter that heats up as it accelerates, as gas particles spiral inward. Friction caused by their incredible speeds heats them to temperatures of millions of degrees. At these temperatures, the gas begins to glow, first with infrared light, then visible light, and finally with high-energy X-rays. The closer the material gets to the event horizon, the more violent and chaotic its behavior becomes. Magnetic. Field lines snap and reconnect like cosmic whips, occasionally launching jets of superheated plasma thousands of light years into space. This is not a gentle process. Each particle of gas experiences its own version of spaghettification as it approaches the point of no return. But unlike our earlier thought experiment of a human falling into a black hole, these gas particles don't fall alone. They're part of a vast, churning ecosystem of destruction that surrounds Sagittarius asterisk like a cosmic hurricane. The scale of this feeding process is almost impossible to grasp. Our galactic monster has more than 4.1 million times the mass of the Sun. Every piece of matter it consumes adds to this already incomprehensible mass, making it even more powerful, even more inescapable. Yet, what's truly unsettling is how efficiently it operates. Sagittarius A** converts matter to energy with an efficiency that makes our most advanced nuclear reactors look primitive by comparison. But perhaps the most disturbing aspect of our galactic monster isn't what it's currently doing. It's what it's capable of doing. Right now, Sagittarius * is in what astronomers call a quiescent state. It's feeding relatively quietly, consuming only small amounts of material. But this giant has the capacity to wake up if a large cloud of gas or, more dramatically, an entire star were to wander too close. Sagittarius * could suddenly become what astronomers call an active galactic nucleus. The feeding frenzy would be so intense that it would outshine every star in our galaxy combined. The radiation released would be visible from billions of light years away, announcing to the entire universe that our quiet neighborhood monster had awakened. Consider the implications of living in a galaxy with an active supermassive black hole. At its center, the radiation would sterilize vast regions of space, potentially affecting planetary atmospheres across thousands of light years. The gravitational effects would disrupt stellar orbits, sending some stars careening into interstellar space while drawing others into deadly spirals. Toward the center, we exist during a cosmically rare period of galactic peace when our central monster slumbers. But deep time reveals a different story. Over the billions of years of our galaxy's history, Sagittarius * has likely experienced numerous feeding frenzies, each one temporarily transforming the Milky Way into one of the most violent and luminous objects in the local universe. The stars that orbit closest to our galactic center tell a story of survival in one of the most extreme environments imaginable. Recent studies of the stars orbit around Sagittarius A* have provided unique opportunities to test general relativity and study dynamical processes near a supermassive black hole, constraining the amount of extended mass within its orbit. These stellar survivors experience gravitational forces so intense that time itself runs differently for them compared to us. As you drift towards sleep tonight, imagine the cosmic dance continuing in the darkness above. Every 16 years, completes another death-defying orbit around our galactic monster. Every moment, wisps of gas and dust make their final journey across the event horizon. Every second, Sagittarius A** adds infinitesimally to its already terrifying mass. We are passengers on a cosmic ship orbiting a monster that could, at any moment, decide to fully awaken. Yet rather than cause for despair, this realization brings with it a strange sense of cosmic perspective. We exist in a universe where such magnificent terrors are not only possible, but necessary. Sagittarius A** and its siblings across the cosmos are the gravitational architects that allow galaxies to form and stars to ignite. Our monster next door is both creator and destroyer, both the anchor that holds our cosmic home together and a reminder of the fundamental forces that could tear it apart. In its quiet hunger and patient waiting, it embodies the beautiful terror of a universe far stranger and more wonderful than our ancestors ever imagined. As unsettling as our neighborhood giant may be, it's merely a whisper compared to the cosmic screams echoing from the early universe out there in the deep darkness. Monsters exist that make Sagittarius * look like a gentle companion. Ancient predators that began feeding when the universe was just a cosmic infant, growing to sizes that challenge our understanding of what's physically possible. In the deep quiet of tonight, as you rest in the safety of a universe that has aged and cooled over 13.8 billion years, imagine traveling backward through cosmic time to witness something that should have been impossible. Picture the universe as it was just 500 million years after the Big Bang, a time when the first galaxies were barely flickering into existence, when space itself was still glowing from the afterglow of creation. In this primordial darkness, something terrifying was already stirring. Black holes so massive and so hungry that they defied every law of physics we thought we understood. Astronomers using the James Webb Telescope have zoomed in on a little red dot that existed just 500 million years after the Big Bang, and found that it may contain the earliest known black hole in the universe. These aren't the black holes we've grown familiar with, the patient stellar remnants, or even the massive galactic anchors like Sagittarius A**. These are something far more disturbing. Primordial monsters that began their feast when the cosmos was still in its infancy. Let your mind drift to that ancient epoch, when the universe was smaller, denser, and filled with pristine hydrogen and helium that had never known the nuclear fire of stars. In this cosmic nursery, monster black holes in the early universe seem to have grown too big, too fast, challenging our fundamental understanding of how such objects could possibly exist. The discovery that has shaken astronomers to their core involves black holes that appear to be breaking the most fundamental limit of cosmic feeding, named LID 568. This 7.2 million solar mass black hole appears to be feeding on matter at a rate 40 times its Eddington limit, and is seen as it existed just 1.5 billion years after the Big Bang. The Eddington limit represents the theoretical maximum rate at which any black hole should be able to consume matter, the point where the outward pressure of radiation from infalling material should halt further accretion. Imagine witnessing such a cosmic violation in person. Picture yourself floating in the primordial darkness, watching as this ancient monster tears apart the fabric of physical law itself. The feeding black hole seems to be eating 40 times faster than is theoretically possible, creating a spectacle so violent and luminous that it outshines entire regions of the early universe. But how? Do you visualize something consuming matter at such an impossible rate? This black hole's feast could help astronomers explain how supermassive black holes grew so quickly in the early universe. Picture streams of primordial gas, still carrying the chemical signature of the Big Bang itself, spiraling into an accretion. Disk so hot and chaotic that it resembles a cosmic hurricane made of pure energy. The material doesn't fall gently into this ancient predator. Instead, it forms towering columns of superheated plasma, reaching temperatures of hundreds of millions of degrees as it plunges toward the event horizon. These feeding streams move so fast that they appear as brilliant jets of light, visible across billions of light-years of space. The sheer violence of this consumption process creates shock waves that ripple through the early universe, influencing the formation of the very first galaxies. Recent discoveries have revealed something even more unsettling about these primordial monsters. An international team of astronomers have used the James Webb Space Telescope to find evidence for an ongoing merger of two galaxies and their massive black holes. When the universe was only 740 million years old, this marks the most distant detection of a black hole merger ever obtained. Envision this ancient collision. Two supermassive black holes, each already impossibly massive for their cosmic age, locked in a death spiral that warps space-time itself. As they orbit each other with increasing speed, they create gravitational waves so powerful that they shake the very foundations of reality. The final merger releases more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. But perhaps the most haunting aspect of these early universe discoveries is what they suggest about the nature of cosmic evolution itself. JWST observations of light sources before the first galaxies should have formed are raising new questions about our galactic origins. We are witnessing objects that seem to have appeared fully formed, like cosmic ghosts materializing out of the primordial darkness. These ancient predators challenge our understanding of how black holes grow. In the modern universe, supermassive black holes like Sagittarius A** took billions of years to reach their current mass, slowly accumulating matter over cosmic time. But these early monsters seem to have bypassed this patient growth, somehow achieving stupendous masses when the universe was barely out of its cosmic infancy. NASA's Webb has found a possible direct collapse black hole, suggesting that some of these primordial monsters might have formed directly from the collapse of massive clouds of primordial gas, skipping the usual stellar evolution process entirely. Imagine clouds of gas so massive and dense that they collapsed directly into black holes, without ever forming stars, cosmic shortcuts that allowed these monsters to achieve terrifying sizes almost instantaneously. Recent research has revealed that numerous red, compact galaxies in the early universe may harbor growing supermassive black holes, creating what astronomers call little red dots scattered across the ancient sky. These aren't gentle, distant lights. They're the feeding signatures of cosmic predators so active that they outshine every star in their host galaxies combined. Picture the early universe as a hunting ground where these primordial black holes roamed like cosmic apex predators. Unlike their modern counterparts, which feed quietly and sporadically, these ancient monsters were in a constant state of violent consumption. They devoured not just occasional stars or gas clouds, but entire regions of space, growing larger and more powerful with each cosmic meal. The implications are deeply unsettling when you consider the scale of destruction. These feeding frenzies represented. Each Super Eddington feeding event sterilized vast regions of the early universe, preventing star formation across millions of light years. These weren't just black holes. They were cosmic population control mechanisms determining which regions of the early universe would be allowed to form stars and which would remain barren. As you contemplate these ancient terrors, consider that we are seeing them as they were billions of years ago. They're light traveling across the cosmos to reach us tonight. But what became of these primordial monsters? Some merged with each other in spectacular gravitational wave events. Others exhausted their local food supply and entered dormant states. And some may have grown into objects so massive and so powerful that they dwarf even our most extreme expectations. The early universe's hungry ghosts reveal a cosmos far more violent and chaotic than we ever imagined. They show us that the peaceful, star-filled galaxies we see today are the survivors of a primordial apocalypse, a time when black holes ruled the universe with an iron gravitational fist, determining the fate of cosmic evolution through their insatiable hunger. These discoveries force us to confront an unsettling truth. The universe's most terrifying predators aren't hiding in distant corners of space or waiting in the future. They were here first, established and feeding before our galaxy, our solar system, or even the heavy elements that compose our bodies had any chance to form. We exist in a universe that was shaped by monsters. Yet out of this primordial violence emerged something unexpected, the seeds of cosmic beauty. The very process that made these early black holes so terrifying also enriched the universe with the heavy elements necessary for rocky planets and organic chemistry. Their violent feeding created the turbulence and mixing that would eventually allow stars like our Sun to form. These ancient giants were just the beginning. The universe was preparing something far more monstrous. In the depths of space, astronomers have discovered objects that make even these primordial predators seem modest by comparison. Black holes so massive that they challenge our understanding of what the universe can physically create. Cosmic giants that outshine hundreds of trillions of suns and reshape reality itself across impossible distances. In the infinite darkness between the constellations Canes Venatici and Coma Berenices, something exists that defies every scale of measurement we've ever devised. Tonight, as you rest in the quiet safety of Earth, light that began its journey over 10.8 billion years ago continues racing toward us. Light that carries the signature of the most massive black hole ever discovered. TON 618 possesses one of the most massive black holes ever found, at 66 billion times the mass of our Sun. shining with a luminosity of 140 trillion times that of the Sun, making it brighter than the entire Milky Way galaxy. To truly grasp the scale of this cosmic monster, let your mind drift to a comparison that stretches the boundaries of imagination. If our Sun were the size of a marble, TON 618's event horizon would stretch 30 to 40 times wider than our entire solar system. Picture this: a sphere of absolute darkness so vast that light itself, traveling at 186,000 miles per second, would take hours to cross from one edge to the other. The Schwarzschild radius of TON 618 extends approximately 1,300 astronomical units from its center, meaning its event horizon is 1,300 times farther from its center than Earth is from our Sun. If you were somehow standing at the edge of our solar system, looking back toward the Sun, and TON 618 replaced our modest star, its event horizon would appear as a sphere of perfect blackness, stretching far beyond the orbit of every planet, consuming space itself in all directions. But perhaps the most unsettling aspect of TON 618 isn't its size. It's its incredible hunger. This hyperluminous quasar represents what astronomers call an active galactic nucleus, a supermassive black hole in the process of consuming matter at such a prodigious rate that the energy released outshines entire galaxies. The accretion disk surrounding TON 618 glows with such intensity that it completely drowns out the light from every star in its host galaxy, rendering billions of suns invisible against the brilliance of this cosmic feeding frenzy. Imagine witnessing such a spectacle from a safe distance, though with TON 618, no distance truly feels safe. The accretion disk would appear as a swirling maelstrom of superheated plasma, rotating at tremendous speeds around the invisible monster at its heart. Material spiraling toward the event horizon reaches temperatures of billions of degrees, hot enough to strip electrons from atomic nuclei and create a sea of charged particles that generates magnetic fields stronger than anything we can conceive. These magnetic field lines don't simply contain the chaos, they channel it, launching relativistic jets of matter thousands of light years into space. Picture twin beams of energy, each wider than our solar system, extending across galactic distances like cosmic lighthouse beams. These jets travel at 99% the speed of light, carrying enough energy to illuminate and sterilize entire regions of intergalactic space. The discovery of TON 618 fundamentally challenges our understanding of how such massive objects could exist. TON 618 was originally catalogued in the Torrent-Sintler survey in Mexico as a blue stellar object, but in the 1970s, spectroscopic follow-ups revealed broad emission lines and a high redshift, confirming it as a quasar. The subsequent mass measurements yielded a staggering estimate of approximately 66 billion solar masses, placing TON 618's black hole in a class of its own. But here's where the cosmic mystery deepens into something truly unsettling. We're seeing TON 618 as it existed over 10 billion years ago, when the universe was less than a quarter of its current age. The light carrying this ancient image has been traveling through space, Since before our solar system existed, before the Milky Way had assumed its current spiral structure, before the heavy elements that compose rocky planets had been widely distributed throughout the cosmos. This temporal displacement raises a haunting question. If Ton 618 was already 66 billion solar masses when the universe was young, how massive has it become today? Over the past 10.8 billion years, this cosmic predator has continued to feed, potentially consuming thousands of stars, entire galaxy clusters, and perhaps even other supermassive black holes. The Ton 618 we observe is merely a ghost, a light echo, from a monster that may now be incomprehensibly more massive. Consider the implications of such sustained growth. If Ton 618 has maintained even a fraction of its ancient feeding rate, it could now possess a mass approaching or exceeding 100 billion times that of our Sun, a size that begins to approach what theoretical physicists call stupendously large. Black holes, at such masses, the gravitational influence extends across truly cosmic scales, potentially affecting the evolution of entire galactic clusters. The physics of Ton 618's feeding process creates a spectacle that challenges our ability to visualize cosmic violence. Unlike smaller black holes that consume matter in relatively gentle streams, TON 618 tears apart entire star systems in massive, chaotic feeding events. Gas clouds spanning hundreds of light-years are accelerated to incredible speeds, creating shock waves that heat material to temperatures found nowhere else in the universe. The energy output from this feeding process is almost impossible to comprehend. TON 618 shines with absolute magnitude of 30.7, radiating 4 times kW of power, equivalent to the energy output of 140 trillion stars like our Sun. This luminosity is so extreme that Ton 618 ranks among the brightest objects in the known universe, visible across billions of light-years of space, despite being a single point source. Yet what makes this brightness truly haunting is its source. Every photon of light streaming from TON 618 represents matter that has been accelerated to tremendous speeds before crossing the point of no return. The brilliant glow we observe is literally the death scream of cosmic material as it experiences spaghettification on an unimaginable scale. Entire solar systems' worth of matter are being stretched, heated, and torn apart every second, their constituent atoms contributing to the maelstrom of energy that makes Ton 618 visible across cosmic distances. The gravitational effects of such a massive object extend far beyond its event horizon. TON 618's gravity influences the motion of matter across thousands of light-years, creating what astronomers call a sphere of influence, where normal galactic dynamics break down. Within this region, stars and gas clouds orbit not the collective mass of their galaxy, but the singular pull of the central monster. This gravitational dominance has profound implications for galactic evolution. TON 618 doesn't just consume matter, it regulates star formation across vast regions of space. The energy released from its feeding activity creates powerful stellar winds that can halt star formation in nearby regions, while gravitational effects can trigger star formation in others. In essence, TON 618 acts as a cosmic thermostat, controlling the life and death of stars across distances that dwarf our local galactic neighborhood. As you contemplate the existence of such a cosmic Leviathan, consider that TON 618 represents only what we can currently observe. The universe may harbor even more massive objects, hidden in regions of space too distant or obscured for our telescopes to detect. Theoretical models suggest that black holes could potentially grow to masses exceeding 100 billion suns, entering the realm of truly stupendously large black holes that could reshape our understanding of cosmic structure itself. The discovery of TON 618 forces us to confront the humbling reality that our universe contains objects so massive and powerful that they transcend human comprehension. This is not merely a large black hole. It's a cosmic entity that challenges our most fundamental assumptions about the limits of physical reality. Its very existence suggests that the universe operates on scales and through processes far more extreme than our earthbound experience could ever prepare us to imagine. Tonight, as you drift toward sleep, TON 618 continues its ancient feast, consuming matter at rates that would drain entire solar systems in cosmic moments. The light from its current feeding activities is already racing through space toward us, carrying information about a monster that has had over 10 billion additional years to grow even more impossibly massive. Yet even TON 618 may not represent the ultimate cosmic horror that physics allows, scattered throughout the universe. Astronomers are discovering objects that push the boundaries of what we thought possible. Black holes so exotic and extreme that they force us to reconsider the very nature of space, time, and the limits of cosmic evolution. In the gentle darkness of tonight, as you rest safely on Earth, imagine looking up at the constellation Centaurus and seeing what appears to be a fuzzy star. This is Omega Centauri, the largest and brightest globular cluster visible in our sky. A spectacular collection of 10 million ancient stars packed into a sphere, roughly 150 light-years across for centuries. Astronomers admired this celestial jewel without suspecting the dark secret hiding in its glittering heart. But recent discoveries have revealed something unsettling. Lurking at the center of this stellar metropolis is a predator that may represent one of the most dangerous types of black holes in the universe. This is the realm of intermediate mass black holes, cosmic hunters that exist in a mysterious gap between the stellar mass black holes we understand and the supermassive giants like TON 618 that anchor galaxies. An international team of astronomers has used more than 500 images from the NASA ESA Hubble Space Telescope spanning to decades to detect 7 fast-moving stars in the innermost region of Omega Centauri, providing compelling new evidence for the presence of an intermediate mass black hole. Picture these 7 stellar refugees racing through the heart of Omega Centauri at speeds that betray the presence of something massive and invisible, pulling at them with tremendous force. The paths of 7 fast-moving stars in the center of the cluster indicate the presence of an intermediate mass black hole. These aren't gentle orbital dances like the planets around our sun. These are desperate flights from a gravitational predator that has already consumed countless companions. With at least 8,000 to 100 solar masses, this is the first intermediate mass black hole to be definitively identified in the center of a globular cluster. But here's what makes intermediate black holes particularly terrifying. They combine the stealth of smaller black holes with a gravitational reach that extends far beyond what their mass would suggest. Unlike the supermassive giants that announce their presence with brilliant quasars, these hidden predators often remain invisible until something ventures too close to escape. Imagine floating near the edge of Omega Centauri's core, watching this cosmic hunter at work. The intermediate black hole doesn't consume matter in the spectacular feeding frenzies we've witnessed with quasars. Instead, it operates more like a patient spider, sitting quietly at the center of its stellar web, waiting for unsuspecting stars to drift within reach of its gravitational influence. When a star does venture too close, the process is both more intimate and more terrifying than the distant consumption we observe in active galactic nuclei. The star doesn't simply fall into the black hole. It's slowly torn apart over months or years in what astronomers call a tidal disruption event. Picture the star's outer layers being gradually stripped away, forming thin streams of stellar material that spiral inward in a deadly ballet. Recent breakthrough simulations have revealed how these hidden predators come to exist in the first place. New research demonstrated a possible formation mechanism of intermediate mass black holes in globular clusters. The first ever star-by-star massive cluster formation simulations revealed that sufficiently dense molecular clouds can give birth to very massive stars that evolve into intermediate mass black holes. Envision the birth of such a monster in the chaotic early days of a globular cluster's formation, when millions of stars are being born in a region smaller than our local galactic neighborhood. Massive stars begin to collide and merge. The first star-by-star simulations of globular cluster formation show that massive star collisions can start a runaway process resulting in the formation of intermediate mass black holes. This isn't the orderly stellar evolution we see in quieter regions of space. It's a cosmic demolition derby where stars smash into each other at tremendous speeds. Each collision creates an even more massive star, which becomes increasingly likely to collide with others. The process accelerates, creating what astronomers call a runaway growth scenario, where a single object at the cluster's center grows rapidly by consuming its neighbors. When this monster finally exhausts its nuclear fuel and collapses, it doesn't form a typical stellar mass black hole. It creates something far more dangerous. What makes these intermediate predators particularly unsettling is their perfect positioning for maximum destruction. Located at a distance of 17,090 light-years from Earth, Omega Centauri contains approximately 10 million stars with a total mass of 4 million solar masses, making it the most massive known globular cluster in the Milky Way. These dense stellar environments create the perfect hunting grounds for intermediate black holes. Unlike supermassive black holes that sit in the relatively empty centers of galaxies, Intermediate black holes lurk in regions where stars are packed thousands of times more densely than in our solar neighborhood. In these crowded conditions, stellar encounters that would be impossibly rare elsewhere become routine events. Stars regularly pass within dangerous proximity of the central predator, creating ongoing opportunities for tidal disruption and consumption. The discovery process itself reveals just how elusive these hunters can be. In 2023, an analysis of proper motions of the closest known globular cluster, Messier 4, revealed an excess mass of roughly 800 solar masses in the center, which appears to not be extended and could thus be considered as kinematic evidence for an intermediate mass black hole. Astronomers can only detect these objects by carefully tracking the motion of nearby stars over decades, looking for the subtle gravitational signatures that betray the presence of an invisible predator. Consider the implications of this stealth approach to cosmic predation. While supermassive black holes announce themselves with brilliant accretion disks and powerful jets, intermediate black holes remain hidden until the moment of consumption. A star system could orbit peacefully for millions of years, unaware that it's slowly spiraling toward an inescapable fate. Recent discoveries have revealed that these hidden predators may be far more common than we ever suspected. In 2021, the discovery of a 100 solar mass intermediate mass black hole in the globular cluster BO to 3G78 in the Andromeda galaxy was posted, revealing that massive intermediate black holes may lurk in globular clusters throughout the local universe. Picture the cosmic implications. If most of the thousands of globular clusters in our galaxy harbor intermediate mass black holes, then we're surrounded by a hidden network of gravitational predators. Each of these stellar cities contains its own monster, quietly consuming matter and waiting for unwary visitors to venture too close to the center. But perhaps the most disturbing aspect of intermediate black holes isn't their stealth or their patient hunting strategies. It's their role as cosmic evolutionary bridges. These objects represent the missing link between stellar mass black holes and the supermassive giants that anchor galaxies. They show us that the path from small to large black holes isn't a gentle, gradual growth, but a series of violent feeding frenzies and mergers that can accelerate black hole evolution in ways we're only beginning to understand. The formation mechanisms revealed by recent simulations suggest that intermediate black holes don't just form once and remain static. One possible origin is the growth of less massive black holes via mergers with stars and compact objects within globular clusters. They continue to grow through a combination of stellar consumption and mergers with other compact objects, potentially evolving into even more massive predators over cosmic time. As you contemplate the existence of these hidden hunters, consider that Omega Centauri is visible to the naked eye from most of the southern hemisphere. On a clear night, you can look up and see the light from millions of ancient stars, knowing that somewhere in that glittering swarm, a predator waits with the patience of geological time. The photons reaching your eyes tonight began their journey before our species existed, carrying no hint of the invisible monster that may have consumed countless stars since that light began its journey toward Earth. The discovery of intermediate mass black holes forces us to reconsider our understanding of cosmic safety. We've grown comfortable with the idea that stellar mass black holes are too small to affect us across interstellar distances, while supermassive black holes are safely contained in galactic centers. But intermediate black holes exist in a dangerous middle ground, massive enough to disrupt entire stellar systems, yet small enough to hide in the stellar communities that surround us. These discoveries are still unfolding as astronomers develop new techniques for detecting these elusive predators. Each globular cluster may harbor its own monster, and each monster represents a unique laboratory for understanding how gravity shapes the evolution of stellar communities. The hidden predators are teaching us that the universe contains far more black holes than we ever imagined, and that the cosmic food chain extends into realms we're only beginning to explore. While we search for these hidden hunters, the universe has been orchestrating even more spectacular encounters. Beyond the patient predation of intermediate black holes lies a realm of cosmic violence so intense that it literally shakes the fabric of space-time itself. The collision of black holes so massive that their final dance creates gravitational waves that can be detected across billions of light-years of space. On the morning of May 21, 2019, at precisely 03:02 29 seconds UTC, something extraordinary happened in a region of space 17 billion light-years away. To black holes, locked in a death spiral that had been tightening for millions of years, finally completed their cosmic dance. In a fraction of a second, they merged with such violence that the collision shook the very fabric of reality itself, sending ripples through space-time that traveled across the universe at the speed of light. Tonight, as you rest peacefully on Earth, the echoes of that ancient catastrophe are still washing over us in the form of gravitational waves, little wrinkles in the geometry of space and time. This was GW1905-1, and it represents something that should have been impossible according to our understanding of stellar evolution. The collision involved two black holes of unprecedented size, one weighing 85 times the mass of our Sun, the other 66 solar masses. When they merged, the resulting explosion converted the equivalent mass of 8 entire suns directly into gravitational wave energy in less than a tenth of a second. To truly grasp the scale of this cosmic violence, imagine if you could witness the final moments of this billion-year courtship. Picture two invisible monsters, each more massive than anything our Sun could ever become, orbiting each other at a significant fraction of the speed of light. As they spiral closer, their gravitational fields become so intense that they begin to distort each other's event horizons, creating a cosmic tornado of warped space-time. The dance begins slowly, almost gracefully. For millions of years, the two black holes orbit each other at distances measured in astronomical units. Their gravitational embrace gradually tightening as they lose energy to gravitational waves. But as they draw closer, the process accelerates dramatically. In the final seconds before merger, they're whipping around each other hundreds of times per second, their combined gravitational field creating a maelstrom that would be visible from billions of light-years away if light could escape from their vicinity. Then comes the final moment, the plunge. In less than 20 milliseconds, two separate event horizons become one. The collision is so violent that it creates what astronomers call a chirp, a distinctive pattern of gravitational waves that rises in both frequency and amplitude. As the black holes spiral together, culminating in a brief, powerful burst. As they merge, this collision produced the first clear detection of an intermediate mass black hole, with the resulting merged object weighing approximately 150 solar masses. A cosmic monster that exists in the previously mysterious gap between stellar mass and supermassive black holes. But what makes GW1905-1 particularly unsettling isn't just its size. It's what the discovery implies about the hidden population of massive black holes lurking throughout the universe. The detection was made possible by one of humanity's most remarkable achievements, the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two widely separated installations within the United States, one in Hanford, Washington, and the other in Livingston, Louisiana, operated in unison as a single observatory, working alongside the Virgo detector in Italy. This three-detector network can pinpoint the source of gravitational waves across the cosmic deep. Imagine the delicate precision required to detect these cosmic ripples. When gravitational waves from GW1905-1 reached Earth, they compressed and stretched space itself by an amount smaller than 1/10 the width of a proton. This infinitesimal distortion was measured across detector arms that stretch for kilometers in length. Using laser interferometry so sensitive that it can detect changes smaller than the nucleus of an atom dot. But the true terror of GW1905-1 lies in what it reveals about the formation of such massive black holes. The 85 solar mass black hole sits right in what's called the parent stability mass gap, a theoretical region where no black holes should be able to form through normal stellar evolution. Stars massive enough to create such heavy black holes should destroy themselves completely in parent stability supernovae, leaving nothing behind. Yet somehow, this impossible object not only existed, but managed to find a companion for a cosmic dance of mutual destruction. The implications are deeply unsettling. Either our understanding of stellar evolution is fundamentally flawed, or these black holes formed through some other, more exotic process we don't yet comprehend. Recent analysis has revealed even more disturbing possibilities. Some researchers suggest that GW1905-1 might represent something even more extraordinary. A black hole merger occurring within the accretion disk of a supermassive black hole. Picture this scenario: two black holes, already locked in their death spiral, falling together into the feeding zone of an even larger monster. The dense environment around the supermassive black hole would accelerate their merger, while potentially creating observable flashes of light. A cosmic fireworks display accompanying the gravitational wave symphony. The detection of GW1905-1 opened our eyes to a universe far more violent than we had imagined. Since then, LIGO, Virgo, and their Japanese partner Kagra have detected over 200 gravitational wave events, revealing a cosmos where black hole mergers occur far more frequently than anyone predicted. The current observing run, 04, began on May 24, 2023, and has been extended beyond its original one-year plan as detectors continue to capture these cosmic collisions at an unprecedented rate. Each detection tells a story of cosmic violence that played out billions of years ago. The gravitational waves we detect today began their journey across space when the universe was younger, smaller, and more chaotic. Some of these collisions occurred when the first galaxies were still forming, when supermassive black holes were establishing their dominance in galactic centers, when the cosmic web of dark matter was still settling into its current configuration. Consider the journey of the gravitational waves from GW1905 to 1. They traveled for 17 billion light-years, crossing a universe that expanded during their transit. The waves that reached our detectors in 2019 began their journey when our solar system didn't exist, when our galaxy was still gathering the material that would eventually form the stars and planets of our cosmic neighborhood. But perhaps the most unsettling aspect of these cosmic collisions is their ongoing nature as you rest tonight. Somewhere in the observable universe, black holes are completing their final spirals. The gravitational waves from these mergers are already traveling toward us at the speed of light, carrying information about cosmic violence that we won't detect for millions or billions of years. The frequency of these detections suggests that black hole mergers are not rare, isolated events, but a fundamental aspect of cosmic evolution. Every few days, LIGO and Virgo detect new gravitational wave events, revealing a universe where massive objects are constantly colliding, merging, and reshaping the gravitational landscape of space and time. Recent theoretical work has revealed that these mergers might occur in cosmic nurseries, dense stellar environments, where black holes can form, interact, and merge with remarkable efficiency. Globular clusters, the accretion disks of supermassive black holes, and the cores of gas-rich galaxies all provide the crowded conditions necessary for black holes to find merger partners. The dance of merging black holes also creates some of the most extreme physics in the universe. In the final moments before collision, matter is accelerated to significant fractions of the speed of light. Magnetic fields reach intensities billions of times stronger than Earth's, and the curvature of spacetime becomes so extreme that it approaches the theoretical limits of what general relativity can describe. As these cosmic dancers complete their final embrace, they don't simply disappear. They birth something new and potentially even more terrifying. The merged black hole often receives a gravitational kick from asymmetric gravitational wave emission, launching it through space at speeds that can exceed 1,000 kilometers per second. These rogue black holes become cosmic wanderers, traveling between galaxies and potentially disrupting any stellar systems unlucky enough to cross their path. The implications extend beyond individual mergers to the evolution of the universe itself. Each black hole collision removes orbital energy from the cosmic web, gradually reducing the chaos of the early universe and contributing to the more ordered structure we observe today. In essence, these violent dances serve as cosmic breaks, helping to stabilize the large-scale architecture of reality. Yet for all we've learned from gravitational wave astronomy, GW1905-1, and its siblings represent only the beginning. The next generation of detectors will be sensitive enough to observe black hole mergers from the very edge of the observable universe, potentially revealing cosmic collisions that occurred when the first black holes in the universe were establishing their dominance. These cosmic collisions pale before the theoretical monsters that might still be hiding in the dark beyond the intermediate mass black holes created by mergers, beyond the supermassive giants that anchor galaxies. Theoretical physics suggests the possibility of objects so massive and so ancient that they challenge our understanding of what the universe can create. The realm of primordial and stupendously large black holes awaits our exploration. Cosmic entities that might predate the formation of the first stars and dwarf even the most massive objects we've yet discovered. In the quiet darkness of tonight, as you rest in a universe that has aged and evolved for nearly 14 billion years, imagine traveling back to the very beginning, to a time before the first stars ignited, before galaxies formed, even before the fundamental forces of nature had settled into their current configurations. In those first moments after the Big Bang, when the universe was smaller than an atom and hotter than we can comprehend, something extraordinary may have been born. Black holes that existed before anything else, primordial monsters that could still be lurking in the cosmic shadows today. Recent breakthrough research has revealed that in the first quintillionth of a second, the universe may have sprouted microscopic black holes with enormous amounts of nuclear charge. Physicists propose these aren't the black holes we've grown familiar with, born from the collapse of massive stars, or grown through eons of cosmic feeding. These are primordial black holes, cosmic fossils from the universe's infancy that could hold the key to one of astronomy's greatest mysteries, the nature of dark matter itself. Picture the universe as it existed in those first impossible moments. Space itself was a seething foam of quantum fluctuations, where the very concepts of matter and energy were still being defined. In this primordial chaos, density fluctuations could become so intense that they collapsed directly into black holes, skipping entirely the millions of years of stellar evolution that normally precede black hole formation. The theoretical framework suggests that primordial black holes formed during the quantum chromodynamics epoch, prior to 10 to 5 seconds after the Big Bang, resulting in a broadly plateautic mass distribution today, with a number of distinct bumps, the most prominent one being at around 1 solar mass. Imagine the universe as a vast ocean of energy, where waves of density occasionally grew so tall that they collapsed under their own weight, creating pockets of infinite curvature in space-time. But here's where primordial black holes become truly unsettling. They could be all around us right now, invisible and undetectable, making up the mysterious dark matter that comprises 85% of all matter in the universe. The gravitational pull from these tiny, invisible objects could potentially explain all the dark matter that we can't see today, suggesting that we live in a cosmos populated by ancient predators. From the universe's birth, consider the implications of this possibility as you rest tonight. Primordial black holes ranging in mass from microscopic to stellar scales could be passing through your room, through your body, through the Earth itself. New simulations suggest that there are enough primordial black holes in the universe for one to pass through the inner solar system every decade, creating subtle gravitational effects that we're only now learning to detect. These ancient monsters wouldn't announce their presence with brilliant accretion disks or powerful jets. Instead, they would glide silently through space, their only signature the gentle warping of space-time around them. A primordial black hole the mass of an asteroid could pass within a few astronomical units of Earth and reveal itself only through tiny perturbations in planetary orbits. A cosmic ghost leaving barely detectable fingerprints on the solar system's clockwork precision. But primordial black holes represent only one category of theoretical terror. At the opposite extreme of the mass spectrum, recent studies have proposed the existence of objects so massive that astronomers have created an entirely new classification for them: stupendously large black holes, or SLABS. These hypothetical monsters would possess masses greater than 100 billion times that of our Sun, making even Ton 618 appear modest by comparison. The theoretical framework for slabs pushes the boundaries of what physics allows. While some studies have suggested that the maximum natural mass that a black hole can reach is typically on the order of about 50 billion solar masses, a 2020 study suggested even larger black holes could exist based on used models. These objects would be so massive that their event horizons could encompass regions larger than our entire local galactic group. Imagine encountering a stupendously large black hole in the depths of intergalactic space. Its event horizon would stretch across hundreds of thousands of light years, creating a sphere of absolute darkness larger than most galaxies. From a distance of 1,000,000 light years, farther than the Andromeda Galaxy is from the Milky Way, this monster's gravitational influence would still be detectable, subtly affecting the motion of entire galactic clusters. Recent observations have hinted at the possible existence of such objects. Astronomers have discovered potentially the most massive black hole ever detected in the cosmic horseshoe galaxy, with a mass approaching 36 billion solar masses, close to the theoretical upper limit of what is possible in the universe, and 10,000 times heavier than the black hole at our galaxy's center. While not quite reaching the SLAB threshold, this discovery suggests that the universe may indeed harbor objects approaching these stupendous scales. The formation mechanisms for such massive objects remain deeply mysterious. Black holes can, theoretically, grow indefinitely if continuously fed, but the universe's age and typical growth rates should limit their size. For a black hole to reach stupendously large masses within the 13.8 billion year history of the universe, it would need to feed almost continuously at rates that approach or exceed the Eddington limit, a process that should theoretically prevent further growth through radiation pressure. This creates a cosmic paradox. SLABS could exist in principle, but they challenge our understanding of how black holes grow and evolve. Their existence would require exotic formation mechanisms, perhaps the direct collapse of primordial dark matter structures, or the merging of multiple supermassive black holes in the early universe. As most extreme environments, consider the implications of SLABS for cosmic evolution. These objects wouldn't just anchor individual galaxies. They would dominate entire regions of the universe, their gravitational influence shaping the large-scale structure of reality itself. Galaxy clusters, dark matter filaments, and cosmic voids could all be organized around these invisible titans, creating a universe where the largest structures are determined by objects we cannot directly observe. The connection between primordial black holes and stupendously large black holes reveals a universe far stranger than we've imagined. At one extreme, microscopic predators from the Big Bang itself could be drifting through our solar system, undetected guardians of dark matter's secrets. At the other extreme, objects more massive than entire galactic clusters could be lurking in the cosmic deep, their very existence challenging our understanding of what the universe can create. Recent theoretical work has explored how these extreme objects might interact with each other and with normal matter. Primordial black holes could serve as seeds for larger structures, gradually accreting matter over cosmic time to eventually reach stupendously large masses. Alternatively, SLABS could influence the formation and evolution of primordial black holes, creating feedback mechanisms that we're only beginning to understand. The search for these theoretical terrors is pushing the boundaries of observational astronomy. Gravitational wave detectors are becoming sensitive enough to detect the mergers of primordial black holes, potentially revealing their abundance and mass distribution. Advanced gravitational lensing techniques might reveal the presence of stupendously large black holes through their effects on distant galaxies and quasars. As you contemplate these cosmic possibilities, consider that the universe may be populated by black holes, spanning an almost unimaginable range of masses, from primordial micro-holes lighter than mountains to stupendous giants that dwarf entire galactic superclusters. Each category represents a different aspect of cosmic evolution. From the quantum chaos of the Big Bang to the large-scale architecture of mature cosmic structure, the theoretical existence of these objects forces us to confront the possibility that our universe is far more exotic and dangerous than we've ever imagined. Primordial black holes suggest that the fundamental building blocks of reality might include invisible predators from the universe's birth. Stupendously large black holes hint at cosmic structures so massive that they transcend our current understanding of gravitational physics. Yet perhaps the most unsettling aspect of these theoretical terrors is their potential ubiquity. If primordial black holes make up dark matter, then the universe is essentially a vast ecosystem of invisible predators, with normal matter representing only a small fraction of cosmic reality. If stupendously large black holes exist, then the cosmic web itself might be organized around objects so massive that they reshape space-time across cosmic distances. The journey through these theoretical realms brings us to a profound realization. The black holes we've discovered and studied, from stellar remnants to supermassive galactic anchors, may represent only a tiny fraction of the gravitational monsters that populate our universe. The cosmos may be teeming with predators we cannot see, cannot detect and can barely imagine, operating on scales from the microscopic to the truly cosmic. As we drift toward the end of our journey through cosmic terror, perhaps the most unsettling question remains. In a universe populated by such magnificent monsters, how do we find meaning and wonder rather than fear? The answer lies not in diminishing the reality of cosmic violence, but in recognizing our extraordinary fortune to exist during a brief moment of cosmic peace, surrounded by protective forces that allow consciousness itself to emerge and contemplate the magnificent terrors that shape reality. In the gentle quiet of tonight, as our journey through cosmic darkness nears its end, imagine stepping back from the individual terrors we've encountered and seeing them as part of a grander tapestry, one where the most frightening predators in the universe are also its most essential architects. The black holes we've feared throughout this exploration are not merely cosmic destroyers. They are the hidden gardeners of reality itself, sculpting galaxies, regulating star formation, and creating the very conditions that allow planets like Earth to exist in islands of tranquility. Recent breakthrough research has revealed something remarkable about the relationship between black holes and their galactic neighborhoods. Scientists have obtained the first clear observational evidence that the mass of the supermassive central black hole in a massive galaxy affects the formation of new stars during its lifetime. This discovery transforms our understanding of cosmic monsters from purely destructive forces into cosmic thermostats, carefully regulating the temperature and activity of their galactic environments. Picture our own Sagittarius asterisk, the 4 million solar mass giant we encountered earlier in our journey. Rather than viewing it as a sleeping predator waiting to devour our galaxy, imagine it as a cosmic conductor, orchestrating the symphony of stellar birth and death across the Milky Way. Through a delicate process called feedback, our central black hole prevents runaway star formation that would quickly exhaust our galaxy's gas reserves, instead ensuring a steady, sustainable rate of stellar birth that has continued for billions of years. The mechanism is elegantly simple, yet profoundly important. When supermassive black holes feed, they release enormous amounts of energy through powerful jets and radiation. This energy heats the surrounding gas clouds, preventing them from cooling and collapsing to form new stars. Black hole-regulated star formation ensures that galaxies don't burn through their stellar fuel too quickly, extending their productive lifetimes across cosmic ages. Recent observations using the James Webb Space Telescope have revealed this feedback process in action across cosmic time. A fast rotator post-starburst galaxy quenched by supermassive black hole feedback at Z equals 3 shows us how massive galaxies were regulated by their central black holes. When the universe was less than 2 billion years old, the most massive galaxies in the universe stopped forming stars due to the time-integrated feedback from central supermassive black holes, creating the diverse galactic ecosystem we observe today. Consider the profound implications of this cosmic relationship. Without supermassive black holes, galaxies would experience runaway star formation in their early years, quickly converting all available gas into stars. These stellar furnaces would burn hot and die young, leaving behind white dwarfs, neutron stars, and stellar mass black holes within a few 100 million years. The galaxy would become a stellar graveyard, devoid of the long-lived, stable stars necessary for planetary systems and the gradual evolution of complex chemistry. Instead, supermassive black holes act as cosmic pacemakers, ensuring that star formation proceeds at a measured rate over billions of years. This regulation creates the perfect conditions for stars like our Sun, modest, long-lived nuclear furnaces that shine steadily for 10 billion years or more, providing the stable energy necessary for planetary atmospheres, liquid water, and the gradual chemical evolution that leads to organic molecules and eventually to life itself. The feedback relationship extends beyond individual galaxies to shape the large-scale structure of the universe itself. Computer simulations of cosmic galaxy development have revealed that details of galaxy development are closely tied to the properties of supermassive black holes, including their masses and feeding rates. The cosmic web, the vast network of galaxy clusters, filaments, and voids that defines the universe's architecture, is fundamentally shaped by the interplay between dark matter gravity and black hole feedback. Recent research on stellar feedback-regulated black hole growth has revealed how this cosmic dance unfolds across multiple scales, from individual star-forming regions to entire galactic halos. The process involves the main phases of supermassive black hole accretion, an early, highly intermittent phase where black holes grow rapidly through chaotic feeding events, followed by a more regulated phase where feedback mechanisms maintain a delicate balance between growth and star formation. But perhaps the most beautiful aspect of this cosmic relationship is how it creates diversity rather than uniformity. Different galaxies, with different histories of black hole growth and feedback, evolve along different paths. Some become massive elliptical galaxies with old, red stars and quiet central black holes. Others, like our Milky Way, maintain active spiral arms with ongoing star formation carefully regulated by their central monsters. Still others experience dramatic merger events that trigger both starburst activity and rapid black hole growth. This diversity is essential for cosmic evolution because it creates different environments for planetary formation and evolution. Elliptical galaxies provide stable, metal-rich environments where rocky planets can form from the heavy elements forged in previous generations of stars. Spiral galaxies like ours offer dynamic environments where new stars continuously form, creating opportunities for planetary system formation across cosmic time. Even the most violent merger events contribute by mixing heavy elements and triggering the formation of new stellar populations. The realization that black holes are essential for galaxy formation helps us understand our place in the cosmic ecosystem. We exist not despite the presence of these gravitational monsters, but because of them. Every atom in your body heavier than hydrogen, and helium was forged in the nuclear furnaces of stars, whose formation was regulated by black hole feedback. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of these elements exist because supermassive black holes created the conditions necessary for multiple generations of stellar nuclear synthesis. Recent discoveries have also revealed how this feedback process operates across cosmic time. Hubble's deep near-infrared observations challenge theories of supermassive black hole formation. By revealing more of these objects in the early universe than previously expected, this suggests that the regulatory relationship between black holes and galaxies was established very early in cosmic history, helping to explain why the universe developed such remarkable structure and diversity. As you contemplate this cosmic perspective, consider the extraordinary chain of events that led to your existence. The supermassive black holes we feared throughout our journey created the galactic environments necessary for star formation. Those stars forged the heavy elements and provided the energy for planetary formation. The planets created the chemical laboratories where organic molecules could evolve into self-replicating systems. And eventually, after billions of years of evolution, consciousness emerged, the universe's way of becoming aware of itself. In this context, our fear of black holes transforms into something deeper: gratitude and wonder. We are not separate from these cosmic monsters, but products of their creative power. The same gravitational forces that can tear apart stars and devour entire solar systems also created the stable galactic environment that allowed our sun to form, our planet to develop its protective atmosphere, and life to evolve the complexity necessary for consciousness. The future of our cosmic neighborhood remains intertwined with the behavior of these gravitational architects. Our own Sagittarius A** will continue to regulate star formation in the Milky Way for billions of years to come. When the Milky Way eventually merges with Andromeda Galaxy in approximately 4.5 billion years, the interaction between their supermassive black holes will trigger new episodes of star formation, while eventually creating an even larger regulatory system. On longer time scales, the universe itself will continue evolving under the influence of black hole feedback. As gas supplies become depleted and star formation gradually declines, supermassive black holes will enter dormant phases, allowing their host galaxies to coast through space. As stellar cities filled with the evolved remnants of ancient stellar populations, yet even in this far future, the legacy of black hole regulation will persist in the stable, long-lived stars that provide billions of years of steady energy. Red dwarf stars, formed during epochs of regulated star formation, will continue shining for trillions of years, potentially providing the energy necessary for life to persist long after our sun has died. The journey through cosmic terrors thus brings us full circle to a profound realization. The universe is not a hostile environment, punctuated by occasional oases of safety. Instead, it is a carefully regulated system where apparent terrors serve essential creative functions. The black holes that initially seemed like cosmic nightmares reveal themselves as cosmic gardeners, patiently cultivating the conditions necessary for complexity, diversity, and ultimately consciousness itself. As you drift toward sleep tonight, surrounded by the gentle darkness of your terrestrial sanctuary, remember that you are a child of the cosmos, shaped by stellar nucleosynthesis, protected by galactic regulation, and gifted with the extraordinary opportunity to contemplate the magnificent forces that govern reality. The monsters we feared throughout this journey are also our creators, our protectors, and our companions in the vast cosmic dance that connects every atom in your body to the most distant quasars and the most ancient black holes. In recognizing this connection, we find not terror but profound wonder. The universe reveals itself not as a collection of separate objects floating in empty space, but as a unified system where consciousness emerges naturally from the interplay of gravity, nuclear fusion, and time. We are the universe becoming aware of itself, gifted with the capacity to appreciate both its creative power and its magnificent terrors. The cosmic monsters will continue their ancient work long after our individual lives end. But through our brief moment of awareness, we become part of their story, witnesses to the grandest narrative ever told, participants in the ongoing creation of complexity and beauty from the fundamental forces that govern reality itself.